Okie dokie. Let's try this. So, I gave you the first notes package for chapter 14, and I gave you the review booklet as well. The first thing I want to say is that the next exam that we're going to do is going to be like a combination of chapter 13 and 14, but it's going to be mostly focusing on chapter 14. So your marks from the chapter 13 exam are up. I've already posted them on Facebook. I've posted them on PowerSchool. We won't be able to do any review sessions until Friday probably, because tomorrow is grade 12 connections. So yeah, grade 12 students, you have connections tomorrow at Flex. Seriously? Okay, so you can talk to me about that at lunch, and then we can figure it out together. Sorry, what was that? Preston, you have the first period spare? My understanding is that you have to go. Yeah. You're going to be double checking my blueprint and making sure that you are on track to graduate, I think, is the idea.
Survey thing that we have to do.
Okay, I think maybe the idea, I'm probably not the person who should be telling you what we're doing tomorrow in Flex, because I'm not going to check out what we're doing tomorrow in Flex until tomorrow at 8 o'clock in the morning, so I don't know, we'll see how it goes. You might be signing up for something called My Pass. Now, in order for you to get your diploma marks, then you need to sign up for My Pass. So if anybody is already signed up for My Pass from last year, then no. No, not
so what you're saying to me is?
What I'm saying to you is I don't know what I'm going to be doing in Flex tomorrow, but I'm going to read a document, it's going to tell me, and then we're going to do whatever that document says. Nah, we're good. So anyways, the review booklet, right, as always, I know it says this booklet is due on at the top of your review booklet, but just never, put never. It's never due, right? Last year I used those as assignments because I thought they were going to be good assignments. But it's 6 pages most of the time, and that's wicked long.
Take them as like an extra marker.
Nah, there are no extra marks in Chem 30. What? What? Yeah, I guess there are bonus marks from the review sessions. So that's your bonus mark. Yeah. Jonas, question. Oh, yeah. And then Jordan and Alex, you probably need the sheets. Yeah. Is that because you both showed up late?
Yeah.
Okay, all right. Did anybody else show up late?
You got a tisk though.
Tisk, okay? A wag of my finger. Yeah, I'm going to give them all to you, Jonas. Perfect.
You broke my knee.
So let's start. I don't have your major assignment printed off, but this unit's only really going to take like 2.5 weeks or something like that. It's not going to take that long at all. So you would be surprised. I don't know, maybe not, but you're probably going to be surprised at how much of the stuff from the previous chapter is carried over. We're still going to need Garoa. We're still going to need strongest oxidizing agent. We're still going to need strongest reducing agent. There's going to be a lot of predicting the reaction in this unit. Like every single question basically is going to be predict the reaction. And we're going to have to draw a buttload of pictures, so hopefully you're okay with that. Are you lazy?
Yes.
Yes, you are. Deal with it. Hey, let's try this. So there's 2 types of electrochemical cells. I want to be very clear. An electrochemical cell involves an energy conversion. What an energy conversion do you think it involves? It's the conversion between electrical energy and chemical energy, right? So there's 2 types of electrochemical cells. The first type is going from electricity to chemical. The second type is going from chemical to electricity. Does that make sense? So there's two types of electrochemical cells, and they both involve this, like either that conversion or that conversion. Type number one, voltaic cell. Voltaic cells involve a change from chemical to electrical energy. This is your typical battery. Any chemical reaction that can provide electricity, we refer to it as a battery, right, basically? But if you remember back to grade 9, which was 3 years ago for some of us, really we should be calling it an electrochemical cell or a voltaic cell. Just think any normal battery. Oh, that's terrible. That's a terrible T. An electrolytic cell is the exact opposite. Now, most of you have batteries on you right now. Would you agree with that?
Yes.
The vast majority of you have batteries on you. And most of the time, your battery is acting as a normal battery, but sometimes it's not. When is your battery not acting like a normal battery? When it's charging. And when it's charging, it's acting like an electrolytic cell. What do you do to charge it? Yeah, you plug it into a source of electricity, and then the source of electricity recharges the chemical energy in your battery. Is that okay? So these two processes are exactly the opposite of each other. An electrolytic cell involves a change from electrical energy to chemical energy. Think recharging a battery. Now that's not the only application of it. That's not the only application of electrolytic cells, but that's probably the biggest one. That's the one that you're most familiar with at this point in time. Any questions? Okay, we're going to dive pretty much straight into it. Electrochemical cells have two major parts. They have an electrolyte and they have electrodes. Think electrodes. You should be thinking solid electrical conductors. Give me an example of a solid electrical conductor.
A lightning rod.
A lightning rod is typically made out of?
Iron.
Iron, sure, yeah. What else could you make a lightning rod out of?
Gold.
Gold, copper, any metal. Think any metal. I want to be very clear about something. If I said silver metal, let's take a look at our data booklet for a second, and let's take a look at silver metal in our redox table, page 7. Let's find where silver is. Silver is about 2/3 of the way up. It's got a half reaction potential of 0.80. When I say silver metal, which one comes to mind? Is it silver plus or silver solid? Silver solid. I need you to be very clear about that. Is that metallic things or elements are always atoms. They have no charge on them at all, right? Okay? When that metal reacts with something, it will turn into an ion. So if I say silver metal, it's silver solid. If I say mercury metal, it's mercury, but this time as a liquid. Right? If I say gold metal, it's gold solid, that kind of thing. Hopefully that's pretty clear. The cells are often split into half cells, and we have half reactions. Jordan.
Sorry, this is completely unrelated.
Okay.
But on our test yesterday, there's a question that had iron gas.
Yeah.
Is that a thing?
Yeah, I don't know. Could iron ever be a gas? Okay, what state of matter is iron typically?
Solid.
Solid. Can iron ever turn into a liquid?
Yeah.
If you melt it.
Smelt.
So, no, smelting is a very specific procedure involving carbon. Okay. Okay. So if you melt it, iron can turn into a liquid. So how could you turn iron into a gas?
Heat it up even more.
Heat it up even more. If you evaporate it, that's exactly right.
I didn't think that was possible.
Yeah, it's totally possible. What?
Wouldn't that be like a lot of energy?
It would be a buttload of energy. Yeah, but you could totally do it.
Can you read it?
What?
Is a buttload a unit of iron?
The buttload is not a metric unit of energy, but yeah, it's a unit of energy. Sure. Anything's a unit of energy if you define it. Okay, let's try this. These cells, these batteries, are often split up into what we call half cells. One half cell will give up electrons. One half cell will accept electrons. So that's interesting. So one half cell, if it's giving up electrons, is that going to be an oxidation or a reduction half cell? If it's giving up electrons, it's going to be an oxidation half cell. The other one that's accepting electrons, is that going to be an oxidation or reduction half cell? It's going to be a reduction half cell. So in one half cell, you have oxidation happening. In one half cell, you have reduction happening. Perfect. Each half cell will contain a half reaction. Predict the reaction given by the following substances. So let's say we put all of this stuff together. Let's say we put zinc ions, copper ions, and water all in the same mixture together. I want you to tell me what kind of a reaction are we going to get? Yes, we're going to get a redox reaction, but I want you to literally predict for me the exact reaction that we will get. And I'm going to be busy doing some stuff. Well, I want you to tell me what reaction we're going to get. Yeah, but specifically what reaction? This plus this gives this plus this. I know you did it too much yesterday. I totally get that. I should have glasses on. What do you think this is? Is this Kool-Aid?
I mean, it might be.
It's
bromothiamine fluid.
It's not bromothiamine. No, it's not Kool-Aid.
What is it?
Are you going to just Google it? Is that why you have your phone out? Oh. Oh, so your mom's texting you in the middle of class.
Yeah.
All right.
Apparently she's in a meeting right now, so she's not doing any better.
Okay. What?
Did you turn your thermometer off?
No, it's on.
Okay.
Yep.
I don't know.
Yep.
Turn it.
Nope, it's streaming straight to YouTube right now.
Seriously? Streaming? Live up or mess up with live broadcast. Imagine saying something really controversial. No?
Does that chemical equation follow the law of conservation of charge?
Yes, one does. No.
No, it does. Yeah.
Oh.
Yep.
I know why.
Okay, what's the first step in predicting a reaction? Shohei, I'm going to ask you another question here in a second, okay? But just to the general audience, what's the first step in predicting a reaction? Perfect, Preston. Preston, what's our strongest oxidizing agent?
Oh. Cu2+.
There you go. What's our strongest reducing agent? So we're going to have our two half reactions, right? The zinc is going to give up 2 electrons. Is this an oxidation or a reduction half reaction?
It's an oxidation.
This is oxidation half reaction. And then the copper 2+ is going to accept 2 electrons and turn into copper solid. Sorry, I should have states of matter here. That's really important right now. Yeah. And so this is, what's happening to the copper? Is it an oxidation or reduction? reduction. It's gaining electrons, right? Perfect. And then if we want to, I mean we should, we're going to make a net reaction, so I just got to add these up. The electrons cancel out, so we get Zn solid plus copper 2 plus aqueous gives you zinc 2 plus aqueous plus copper solid. Perfect. Okay, so that's going to be our net reaction. But here's the deal. The zinc and the copper 2 plus don't actually have to react with each other. They don't have to come into contact with each other. I'm going to show you what happens when we have copper 2 plus ions. That's why the solution is blue, because it's copper 2 plus ions. And here's a strip of zinc. Now what's going to happen is, maybe I'll do this with a little bit of sandpaper. Oh, that's terrible sandpaper. Okay, so I tried to make the top part as shiny as possible, right? It's kind of shiny, a little bit shiny. Perfect, no problem. So as soon as I dip the zinc inside the copper, what reaction should happen? This one. Copper should steal the electrons from the zinc. So we're going to get copper metal plated on top of the zinc solid, or this we're going to get zinc ions and we're going to get copper metal. So let's try this out. I'm going to dip it in for like a half a second. I'm going to pull it out and I want you to tell me if you saw any differences. 3, 2, 1, go.
Yeah. Move it over here. It's wet.
It's wet. What do you mean it's wet? Did anything happen to it? It got super dark. We made a new substance right now. Now, the problem here is that this is copper that's been plated on here, but the copper is really quickly oxidizing in the water as well. So you're going to get some sort of a copper oxide formed there. So this reaction is absolutely happening, but the problem is the electrons went straight from the zinc metal straight into the copper solution. So can we use this particular thing to drive like your cell phone? No. Yeah, shut up. To operate your cell phone. Because the electrons went straight from the zinc straight into the copper ions. They weren't forced to go through a specific path. If we want to drive your phone, okay, if we want to operate your phone, we have to force the electrons to go through your cell phone. Does that make sense? No? All right, whatever. These two half reactions, they don't have to be in contact with each other. As long as the electrons can flow from one reaction to another, the reaction will proceed. So let's draw this. Let's kind of make this into a situation where we can force these two things to interact and force electrons to flow from one to the other. What you got to do is you got to draw two beakers. In one beaker, we're going to put copper metal. So this is the way I like to draw. We have copper solid. And what solution should I put with the copper?
Oh wait, water.
I should actually put the copper ions with the copper. Because that way we guarantee they're not going to react with each other. Does that make sense? Copper ions and copper metal will not react with each other. And so we're going to put in here, we're going to put our solution of copper 2 ions. On the other side, well, what's the other substance that we have to react this thing with? We have to react it with zinc. So in here is going to be zinc solid. And what should we put in the liquid here? We should put zinc ions, just to make sure that we don't have a reaction. Zinc 2 plus aqueous. Now the problem is, if I want to transfer electrons, right? Sorry, let's go back for a second, just a quick second. Who's giving up electrons here, the zinc metal or the copper ions? Who's giving away the electrons? The zinc is becoming positive, so it must be giving away electrons, right, Matthew?
Yes.
Yes, good. Okay, so the zinc is giving away electrons. So how do we make sure that the zinc metal can give away electrons to the copper solution? How could we connect these two to allow electrons to transfer from one to the other? A wire. That's all we need. Because wires carry electrons, right, for electricity. So all we have to do is connect this thing. I'm going to put a voltmeter in between them as well, so that we can read the potential difference. And we're almost there.
Kind of wire though.
Doesn't matter. Any electrical conductor. Any electrical.
Copper
Are we
wire.
going to be
It won't
playing
do
with
anything.
wires?
Could be a copper wire. Are you going to be playing with wires?
Yeah.
You're going to be using some form of a wire. Yeah.
It's gonna be like
dangerously. No, it's not going to be dangerously anything. Okay, so here's the problem. If I have electrons, are electrons negative or positive?
Negative.
Electrons are negative. If I have electrons being transferred from the zinc to the copper, then they can flow down through the copper into the copper solution, right? So the electrons can be transferred from the zinc into the copper solution this way. But is this going to make a good, proper cell? Let's try it out. I'm going to put copper. So I've got copper, and I'm going to put it in my copper solution. Awesome, fantastic. I'm going to put zinc, and I'm going to put the zinc ions into the same beaker as the zinc. I just need to clean this off. Just give me a second.
Where's your secret glass?
Okay, good. So what I'm going to do is I'm going to connect one side of my conductive wires to the copper, and I'm going to connect the other side. So let's see. I want you to tell me what's the voltage reading right now, since it's not connected. 0.0 should be 0.0, and it's fluctuating between 0.00 and 0.01. But that's only because
The air is
no, that's only because this thing is not very accurate, and it's reading a little bit of background noise is what's happening. Okay, so what's going to happen? As soon as I touch this to the zinc, what's going to happen to the voltage? Okay, ready? 3, 2, 1, boom. What happened to it?
Nothing.
Oh. You don't have to connect it with another wire, but you do have to do something. Is this circuit complete? No, it's not a complete circuit. If you have charged particles, electrons, if you have charges transferring from one side to the other, you have to have a way for other charges to be transferred the opposite way. Does that make sense? So we're not going to use another wire. We're going to use something called a U-tube.
YouTube.
What?
That's just another one.
Mr. Walton YouTube?
No, not a Mr. Walton YouTube. We're going to be, hey, what's this?
A tube shape.
It's a tube in the shape of a U, right? So we're going to use a U-tube, and we have to fill it with some sort of a conductive solution. We have to fill it with an electrolyte. An electrolyte is a solution that can conduct electricity.
Gatorade.
No, we're not going to use Gatorade. We're going to use a non-reactive solution.
Would that Loki work though?
What?
Would Gatorade Loki work?
Gatorade would probably work, I think.
We should test that
I
out.
know.
No eating of child.
Sir, be careful. You don't want to get chemicals in your mouth.
I think you're doing it on your hand as well.
Yeah, but it's non-reactive, so we're good to go.
Like, what if it was like you put the wrong one and it was like very acidic?
If it was super reactive,
Yeah.
then I'd be boned, I guess. Whatever. Okay, let's try this out. So let's take a look at it. Did you say it'd be awesome? Okay. Let's try this. I want to connect my two solutions, and I want you to focus on, as soon as I put this in there, I want you to focus on what happens to the voltage. 3, 2, 1, go.
Oh yeah.
Did it change?
Yeah.
0.8.
I can't see that far.
Is it saying, okay, but it changed from 0.00 to 0.87. And if it's negative, okay, if it's negative, all you have to do is switch the leads. That's all you have to do. And then it will read a positive voltage. There we go. So is this reading a positive voltage?
Yes.
Okay, perfect. Woo! Good to go. So in here, this thing is typically called
YouTube. Oh, I remember this in grade 9.
it is a salt bridge. And the salt bridge has to be filled with an electrolyte.
Grade 8.
Usually some sort of salt. Right now we're using sodium nitrate. Sodium nitrate is an ionic compound. Ionic compounds we call salts. So all it needs to be filled with is positive and negative ions. So let's think about this. If the electrons are heading towards the copper, does that mean the copper electrode, like, what if the electrons are heading towards the copper, what should the negative ions in the salt bridge do?
Go the other way.
They should go the other way. I don't know if that makes sense to you, but it's the charges should be kind of going in a circle. You should complete the circuit. Okay, we're going to talk a lot more about this. You're going to have to draw probably close to 30 of these diagrams in the next 2 weeks. So just get used to drawing these diagrams. It's just the way it goes. Don't worry about it. Okay.
Are we doing a lab?
Yeah, we are going to be doing a lab. Now, the other thing, instead of using a salt bridge, what we could do... No, not a second wire. We're going to use. We could use something called a porous cup. Now, a porous cup is unsurprisingly, it's a cup. Okay, yeah, and it's porous. What does that mean?
It's pores.
It's got pores in there. What does having pores having? What does that mean? It's like a sponge. It's got little tiny holes in there. So what we could do, instead of doing this. Okay, instead of using the salt bridge, that's some janky little salt bridge, whatever, okay? What we're going to do is I'm going to pour the copper into a different beaker. I'm going to put the copper in that same beaker. Then I'm going to pour the zinc solution inside the porous cup. And so because there are pores in here, when I add them to each other, the electrolytes, now the ions can go straight from one cup to another. Okay? And so as I don't need a salt bridge because the porous cup is acting as my salt bridge now. It's acting as the ability to...
Wouldn't that just like mix them if it's just pores?
It totally would eventually. Do you agree, Marcus, that eventually the ions would start to mix together?
Yes.
Yes, they would, right? And that's I don't want to say it's perfectly fine, but it's part of the design of this cell over the other ones. Okay? So you don't need a salt bridge if you have a porous cup. Now let's take a look at this. Let's think about this for a second. Do you agree there are two electrodes in here? There are two solid metal conductors.
Yeah.
Yes, we've got a we've got a copper one and we've got a zinc one. They are called very specific terms. They're called the cathode and the anode. And do you remember when I said GROA, we were going to add another letter to it?
That was Guerrero.
You really just messed up.
This is if you learn anything from this unit, I need you to learn this. I need you to have GERCOA burnt into your memory. Let's go through what GERCOA stands for. What does it stand for? Gains electrons, reductions. So what happens at the cathode? Reduction. There's a reduction half reaction occurring at the cathode. And what entity is at the cathode? The oxidizing agent. Good. So at the cathode, we get our reduction half reaction. Because we have the reduction half reaction, that's where the oxidizing agent is. We call it the cathode, and Kate, a reduction half reaction, is that gaining electrons or losing electrons? Gaining. It's gaining electrons. What would gain electrons? Do you think something that's positive would gain electrons, or something that's negative would gain electrons? Positive. Something that's positive. So we call it the positive electrode. It's the positive electrode because it's attracting electrons. Another way to think about it gains electrons, so it must be positive because it's gaining electrons, right? Reduction occurs there, it's gaining electrons, it's the cathode, it's the oxidizing agent. But also, what's the first three letters in cathode? Cat. And cats have so is the cathode positive or negative? It's positive. Never do that again. Okay, all right, whatever. Hopefully you never forget that for the rest of your life. So.
Every time you say cat,
yeah,
you have to do that.
Yeah, it's the cathode, right? It's cats have pause. What?
I was on YouTube to watch cats have pause.
Yeah, we're what? I don't know. I don't even know. We're 30 minutes into this. Yeah.
Do you think you could take that video and trim it and post it on Google Classroom for us?
That's the part where you're going.
It's on YouTube. Somebody could make a GIF out of it if you wanted to.
We'll make you
Viral famous. I don't want to be viral famous. Because that seems like a terrible life to live. Yeah. That's exactly right. Instead of being, oh, you're that science teacher who was actually kind of, it was an interesting science teacher, you're going to be like, oh, hey, look, it's the real guy. No, that's the worst life math. Okay. So GERCOA is gains electrons reduction cathode oxidizing agent. Let's think of everything that's the total opposite of this. Okay? Instead of gaining electrons reduction, what would we say? Losing electrons, oxidation. And then it occurs at the anode. And what exists at the anode? The reducing agent. That's why GERCOA is easier to remember than LEUR. If you want to remember LEUR, that's fine. I don't really care.
What's your sound for this one?
No, I don't have a sound. Okay, this is the only one. It's not nearly as good as Cats Have Paws. I did Cats Have Paws first because it's better. The idea is what do you have on your farm? Ants. You have cats, and you have an ox.
Are you joking?
Yeah, that's so just don't worry about it.
You gotta make, no, you gotta make a.
Yeah, I don't know. Because cats, really the true saying for this is that you've got a red cat, so reduction occurs at the cathode, and then you have an ox, so oxidation occurs at the anode, really. And so what do I say? This is what I say this all the time to my Science 20 students, because they do redox in Science 20 as well. And I say, what do you have on your farm? And they're like, every single time they just look, so they're totally blank, and I'm like, you have a, and they're like, an ox and a red cat. So you have an ox and a red cat. And then we say cats have paws. So.
Stop it.
I'll just stick with cats.
Yeah, cats have paws. Okay, the anode. What reaction happens at the anode? Oxidation. Okay, the oxidation half reaction. Because the oxidation half reaction occurs at the anode, what agent is there? It's the reducing agent. And because the cathode is the positive, then that means that this one is the negative.
Do you have a thing for that?
No.
Really?
Yeah.
You have an ox, but you don't have negative.
Yeah. Anox. I don't know. What does an ox say? No. What else would an ox say? I don't know. So it's the negative electrode. How do you know the anode is the negative electrode? That's because it's repelling electrons. Electrons are repelled by it. Yeah, that's terrible.
Oh.
No. Okay, so what I want to ask you is electrons are always transferred from what to what? Where do electrons leave? Do they leave the anode or do they leave the cathode?
They leave the anode.
They leave the anode and they go towards the cathode. So you can think of electrons as going from A to C. That's kind of the idea. Anyways, whatever. So let's think of a proper electrochemical cell. So here's our zinc in our zinc half cell. Here's our copper in our copper half cell. And hopefully you can read it. Can you read the two half reactions underneath the beakers here?
Yes.
Yes.
Yes, you can. Good. So what's happening? I want you to take a look. What state of matter are we starting with at the anode? What state of matter are we starting with? Solid. Zinc solid, and what does it turn into? Zinc 2+ ions. So what's actually happening is tiny chunks, right? These tiny microscopic atoms, they're turning from a solid into aqueous. So they're leaving the electrode. What's happening to the size or the mass of this electrode?
Reduced.
It's the mass is getting reduced, which is you can think of it as it's losing mass. So we could go back and we could say at the anode we are losing mass. What? Okay. So let's take a look at the other half reaction. Let's take a look at the copper half reaction. What state of matter are we starting with at the copper half reaction? Aqueous. So it's an ion floating around in the water. And then what do we end with? Solid. So that ion is joining the electrode. You're getting more and more and more copper atoms plated on the outside of the electrode. So what's happening to the mass of the electrode? It's getting bigger. It's increasing. So we increase the mass, or we gain mass.
So like if you were just to leave it in there, would you just like just heat the entire thing and just be visibly bigger?
Yeah, these are electrodes. These are electrodes that you would find in an electrochemical cell, in specifically a Voltaic cell, because this thing's producing electricity for us to use. So this is the size, right? This is the size or the diameter of the zinc electrode. And then when it was submerged in water, what happened to the size of the zinc electrode? Yeah, because these atoms, these zinc atoms are leaving and joining the solution as ions. So if tiny little bits are leaving that electrode, over time it's going to lose a lot of mass. What would happen if I left this thing in there for an indefinite period of time? It would totally disappear all the way up to the level of the water, right? It would completely disappear.
And then it would drop.
And then, well, yeah, or little tiny chunks would fall off, but then eventually, well, if they're not connected to the conductor, then they would just sit there. But so what's happening to the copper electrode? It's getting bigger because these ions, the ions are floating around in the solution, and when they gain electrons, they join and turn into atoms. Sanja.
So does the zinc anode, does that mean that it's like aqueous and it's like?
Okay, is this a solid element,
Yes.
chunk of
Yes.
zinc? Yeah, it is, okay? And when it reacts, when these atoms give up 2 electrons, they turn into ions. And those ions can be dissolved by the water that's surrounding them. So when the atom turns into an ion, all of a sudden that ion is able to be dissolved by the water and it can leave the electrode.
So if I just put like a zinc like block in,
Yep.
what's the ions here?
Well, what's actually reacting? Is it the metal or is it the zinc ions that are reacting in this half cell? What are we starting with in our half reaction? Zinc solid. It's the zinc solid that's reacting. Over here, what's actually reacting? Is the copper metal reacting or are the copper ions reacting? The copper ions are reacting. So Sanjana, like we had before, if you put a solid chunk of zinc into copper metal, which is what I did when I just dipped it in really quick, if you put the solid zinc in with the copper ions rip away 2 electrons off of the zinc atoms. The atoms turn into ions, those zinc atoms turn into ions, and then all of a sudden they can be dissolved by the water that's surrounding it.
Okay.
Does that make sense?
Yeah.
Yeah. Okay, there's a really quick way of being able to describe what this cell looks like. And this is what we call cell notation. So on the left-hand side, which is usually the anode, typically that's the anode, we'll go zinc solid, comma, or sorry, not comma, zinc aqueous, and then copper 2 ions, copper metal. This is a way of representing what's going on up here. A single line represents a change in the state of matter. So we go from a solid, the zinc solid, and then in the solution we have zinc ions, so we'll separate them by a line. And then the double line represents a boundary like a porous cup or a salt ridge or something like that. So here, hopefully you can clearly see we've got our anode. Well, our anode is the zinc metal, but this is what's happening at the anode, and this is what's happening at the cathode. But specifically, it's the chunk of metal that is the anode or the cathode. I don't know, hopefully that makes sense. I feel like I didn't describe that very well, but on the, there's the 2 double lines, and they separate the the oxidation half reaction from the reduction half reaction. Yes, Groma.
What does the single line do?
The single line just represents a barrier between a state of matter. Like up here, we've got a solid inside an aqueous solution. So I'll just say you've got a solid and an aqueous solution. But they're still together on the same side, on the same half cell. Okay, so what I would like you to do, I would like you, try and answer these questions. The last two questions are going to be the hardest for you to answer, but I want you to try and answer these questions based on that previous slide. And I'm going to be going around answering people's questions. Yeah, Joe.
Because he got it all in a big bin, and that much was in the bin.
Which electrode is
Okay.
Oh, and
You want to start? Let me know, like,
really? No. I just have to show up.
Yeah, you should.
I could just show up and then leave.
No, you gotta show up.
But then I didn't have any.
Yeah, you gotta work hard for that bonus mark. Yeah, but which specifically? Which Yeah. Now, what? Sorry, no.
I don't know.
Okay. So that's
Let's go to the next question.
but it's not the entity. I'm referring to
It's the easiest thing to do.
substance. I think it's
I think I know.
So what's
but,
the-
it just looks weird.
This thing is losing. Yeah, this thing is definitely not seeing. So that's what it's answering.
What? Okay,
Right?
yeah, that's like not last year.
Okay, which electrode is gaining? When I say which electrode, your answer is either the copper metal or the zinc metal. Because the electrodes are the solid chunks of metal. So the copper metal.
So this is C.
What would happen if this all?
Good.
It was stuff like that because we stop the can ions. Yeah, because there's no way for the ions back or the ions to travel. Right, because it's not it wouldn't be back to anymore.
The salt bridge. What that means is why you stop
All the time. All the time.
It's just jokes. Anyone else? You are not good to fix all the world. I see.
Yeah, no reaction. And we give you another 20, 30 seconds. Okay, let's think about this. Bring your attention back towards the front, please. So we're going to answer these questions based on these cells. Get off your phone. We're going to answer these questions based on these two half cells and the way they're operating right now. So what we want to do, what entity, whenever I say entity, I mean specifically what substance. You have to tell me an element with its charge or no charge and its state of matter. So which entity is being oxidized? Well, what is the process of oxidation? Coa. So what is the process of oxidation? That's where we lose electrons, right? So which one of these, let's look at our half reactions. Is this an oxidation half reaction or is this an oxidation half reaction? The other one, the zinc. So the zinc solid, would you all agree the zinc solid is losing electrons turning into zinc ion?
Yes.
Yes. Okay, good. Oop. So it's the zinc solid that's being oxidized. Now what's being reduced? Reduction is gaining electrons. What substance, what entity is gaining electrons? The copper 2 plus, right? The copper 2 plus aqueous is gaining electrons. That's the substance that's being reduced. So far, was that okay?
Yes.
Yep, as long as you kind of know what's being asked of you. Which electrode is gaining mass and which electrode is losing mass? Now this is a little bit ambiguous. There's two potential answers. You could either say cathode and anode, which is a very generalized answer, and sometimes you won't have that option, right? But in this case, which electrode is gaining mass, the cathode or the anode? It's always the cathode. It's always the cathode. Maybe not always, and we'll come to a couple examples of where that's not always the case, but that's fine. So, are we making a solid at the cathode? Then what that means is that this chunk of solid will get bigger and bigger and bigger. Do you agree? Because we're making a solid, and so it's going to get bigger and bigger and bigger. And so I would suggest to you that either the copper solid or you could say the cathode is going to be gaining mass. Which electrode is losing mass? Again, there's kind of two potential answers. The zinc, or you could call it the anode, right? It's always the chunk of metal that's the cathode or the anode, okay? Whenever I say which thing is the cathode or which thing is the anode, you have to refer back to this solid conductive piece of material. Are electrons leaving the cathode or are they leaving the anode? Which one? They always go from A to C, right? So they're always leaving the anode, going to the cathode. What would happen if the salt bridge was removed? Reaction would stop because all of a sudden you've stopped. You've opened your circuit, is a way of saying it. You don't have a complete circuit. So the reaction stops. Halted temporarily. Which electrode are the cations moving towards? Now this one's These two questions are the hardest two questions to ask in my mind, or answer, sorry. What I want you to focus on, does anybody know what the word cation is?
Yeah.
It's a positive.
Positive.
Right? Okay. So cats have pause. A cation is a positive ion. So where do you see positive ions in here? I mean, a little bit of everywhere. You've got zinc positive ions here, you've got copper positive ions here, and you also have positive ions in here. Now, what I want you to think about is, as the electrons are going towards our positive electrode, the electrons combine with something positive. Do you agree with that? Okay. So, not only are we getting more negative, but we're losing positives in here because the electrons come over here and they start getting rid of the positive charge. So there's an absence of positive charge over here. So the positive ions, the cations, will fill its place. The cations, which electrode did they go to? Did they go towards the cathode or the anode?
Cathode.
The cations go towards the cathode all the time, every single time. In this particular case, in this one case, right, which electrode are the cations moving towards? It happens to be copper. So the copper metal, but it's always the cathode. And then we could kind of reverse the idea. Which electrode are the anions going towards? What's an anion? A negative ion. So the negative ions are going to head towards the zinc. Yeah. Always the anode. Okay. I apologize about taking so long. Would you agree we spent a long time on that? Yes. But those are the fundamentals of electrochemical cells. I basically gave you, with exception to one thing, I basically gave you all the information you need to know about like half of this unit when we covered it in about 50 minutes. Okay? So what I would like you to do is I'd like you to draw a silver and lead voltaic cell, and I want you to give the spontaneous reaction that occurs.
Do you want a porous stuff or a...
You can do whatever you want, but I find it easier to draw two half cells and a salt bridge.
Okay.
I find that easier to draw. On one side, you're going to put silver. On one side, you're going to put lead. Hey, what ions are going to go with the silver metal? Silver ions, right? Hg positive. What ions are going to go with the lead metal? Pb2 plus ions, lead 2 plus ions. Remember that you always pair up the silver with the silver, and you always pair up the lead with the lead. Draw your two half cells, connect them with a salt bridge, connect them with a wire. Yeah. Whatever you tell me. Okay, some people are having a little bit of a hard time figuring out, okay, what ion would I pair up the lead metal with? And the easiest explanation I can give you for that is, let's find lead metal. What do you know, what type of lead do you know is not going to react with this lead metal? Pb2+. So that's the type of ion that I would pair with the lead. So Pb2+ is in the same container as the lead, and the silver is in the same container as the silver ions, the silver 1+ ions. So you have to connect them. I don't know, out of habit, just draw a voltmeter. You don't have to draw a voltmeter, that doesn't matter. And then inside your salt bridge, it doesn't matter what's inside your salt bridge as long as it's a non-reactive salt. So a very unreactive salt. Usually we're talking about sodium nitrate, because sodium ions are such a weak, or potassium nitrate. Sodium ions and potassium ions are such weak oxidizing agents that they almost never come into play. Yeah.
Would it make a major difference if you reverse the silver on the side?
So if you put this cell, this beaker on this side, and this beaker on that side, as long as you kept the silver with the silver and the lead with the lead, it makes no difference. Because then you're just kind of looking at it from the opposite perspective. That's all you're doing. Okay, what I want to know, which one of these is the strongest oxidizing agent, and which one of these is the strongest reducing agent? Macy? So the Pb solid is going to be the strongest reducing agent. I agree with you. And what's going to be the strongest oxidizing agent? The silver ions is going to be the strongest oxidizing agent. So we should be able to identify our two half reactions. If this is our strongest oxidizing agent, then let's write that half reaction. Underneath it, I'm going to write that half reaction. We have silver ions reacting with an electron to make silver metal. And over here on this side, what reaction am I going to have?
You're going to have Pb2.
I'm not going to start with Pb2+, right? You're going to start with your strongest reducing agent on one side, and you're going to start with your strongest oxidizing agent on the other. So Pb solid is turning into Pb2+ plus 2 electrons. Now, hopefully this makes sense to us, because one of these has to be an oxidation reaction, and one of these has to be a reduction half reaction. Which one is the reduction half reaction? Which one of these looks like a reduction half reaction to you? This one, right? This one, so the Ag plus is getting reduced because it's gaining electrons. So if this one is the reduction half reaction, which one is my cathode and which one is my anode?
AG would be cathode. And UV would be the anode.
What's the only word I want you to remember? Gurkoa, right? So reduction occurs at the cathode. So we will call the silver solid the cathode, and we will call the lead the anode. Does this make sense? How we can, from the half reactions, you can do anything. As long as you have the half reactions, you can identify anything about this thing. Which side is gaining electrons? Look at this. Do you see how the silver ions are gaining electrons? So this cathode must be gaining electrons. Which side is gaining mass? Is the left side gaining mass or the right side gaining mass?
The left side.
Why is the left side gaining mass?
Because since we're losing electrons on the right side, it's also taking mass.
Okay, so you're losing electrons on the right side. That means we're taking a solid and turning it into aqueous. So this must be losing mass, right? Because we're losing solid. Here, we're making solid, so we must be gaining mass there. Do you understand how we can do whatever we want from the half reaction? We still haven't even answered the question yet. What was the question? Give the spontaneous reaction. What's the lowest common multiple of electrons? Between 1 and 2. 2. So we need 2 Ag plus for every lead.
You forgot the solid.
I did. Perfect. Does that make sense?
Yeah.
Okay, I know that this was a lot, like a mentally, a lot of information was uploaded into your brains today. And so we're going to work on this slowly but surely over the next couple days. We're going to work on this. It'll be fine, don't worry. Again, reminder, tomorrow is connections for grade 12 students.
Great.
Yeah, that's right.
So maybe that's where I'll go with it.